Hello and welcome to another Advent of Code video. This is for day 11. This one's quite a long one, so we're just going to jump right into it. Alright, so the input of the puzzle is a map of seats on a plane, and they are either occupied or present or an aisle. And the problem is kind of like a Conway's Game of Life problem. Let me show you the input. If you're not familiar with Conway's Game of Life, you can open up Wikipedia, but basically it's a tile-based game which has rules for how things move around based on a previous generation, a zero-player game. There's kind of neat things that happen with Conway's Game of Life where, you can build these, I forget what they're called, like gliders, and I don't know, there's a whole bunch of named patterns because it's, kind of a, the oscillators, blinkers, toads, beacons, boats, etc. But anyway, it's kind of a cool little thing. But this is a different Conway's Game of Life, so it's kind of, different. And the way the puzzle works is if you are an L, that means you're unoccupied. And if there are no occupied seats around you, it becomes occupied, which is the octothorpe here. And if you are occupied and there are greater than or equal to 4 occupied around you, it becomes unoccupied. And when it talks about around you, it means the 8 squares around you. So if you're this position here, these three, and then these 2 all count for being around you. So it's like Minesweeper. But anyway, this puzzle is going to oscillate and then eventually get to a steady state. And as soon as it gets to a steady state, you count how many seats are occupied at the end there. And part 2 is very similar to that, except seats have vision, so they can see as far as possible, and both in the diagonals and in the ups and downs. So if we looked at this seat here, it's going to see over to this edge, not see an occupied seat over there. Of course, this is not occupied, but you can imagine if this was. It's going to see up and see off the screen up here. It's going to go to the left and see this one. Again, it can't see through unoccupied or occupied things, so that's where the occupation stops. And it's going to look down and see this one. It's going to look diagonals and see these 4. But yeah, that's how part 2 is going to work. And part 2 is basically the same as part 1, except we'll change this 4 to a 5, so we'll have to adjust some code there. I'm going to show you 2 different ways to solve part 1, but we're going to use the second way to solve part 2 because part 2 is actually too slow to solve using the brute force, or at least I couldn't find a solution with brute force that solved it. So anyway, let's do the parsing first. The way I'm going to represent this is a list of lists of 1 length string. So this is going to be list lister. And fortunately, we can do this with a list comprehension. We can actually call list on a string itself, or line in s.split lines. And what that does is list of a string will give you, one character pieces here. And we'll be able to use that to solve the rest of the puzzle. But anyway, this is the parsing. Parsing's pretty straightforward. And then 3 parsing. And you can see we end up with this map here. It's raining outside, so sorry if you hear the raining noises. But anyway, that's parsing. Let's move on to part 1 down. And the way that I thought about this, I've just simplified the input here. The way that I thought about this is we basically need a loop that continually runs until we've finally gotten to our final solution. And we basically need to loop forever until that is true. And we're going to use parts. Actually, we'll call this prev. So this will be the previous list. That way we can compare against it to see whether we are done or not. And so we're going to build up a new set of lines. And we're going to loop through everything in the previous to generate those lines. So we have to do for line in priv, and then for character in line. And actually what I'm going to do here is I'm going to use enumerate to get us our y and x coordinates here. That way we can look around those positions to see everything that's around it. And so for this, when we're looking at a grid here of 8 things, and this is our current position, we kind of want to look up, down, left, right, and then the diagonals. And I actually simplified mine a little bit by using 2 loops. You can kind of think of this as -1 and 0 and +1, and do the same thing in the y direction. So that's how I'm going to do this here. So super nested loops here for y sub I, or d sub y, so the difference in y, in range -1 to 2, So this, actually, let's not write it as a range because that makes it harder to understand. -1, 0, 1. And then for dx in -1, 0, 1, we basically want to count how many occupied around there. So we'll say occupied equals 0, and we'll do a loop around this. Now note we have to skip if we're either out of bounds of the list or if we're looking at 0, 0, because that's our own piece. And so we'll say, and actually, yeah, we'll do that. So we'll say if, well, we'll say y sub I equals y plus dy, and x sub I equals x plus dx. So that'll give us our new coordinate pair here. And we can say if a bunch of conditions. If dy equals dx, or does not equal dx, so we want this condition here, and y sub I is greater than, well, 0 is less than or equal to y is less than length of prev, so this is whether y is in bounds. And we can also do the same thing for x. 0 is less than or equal to x sub I is less than len of line. So these are our conditions as to whether things are in bounds. And then finally, we need the condition that it's occupied. And prev y sub I, x sub I is equal to this. Then we are going to increment our occupied. Occupied plus equals 1. This is all just to count the number of occupied squares around the current position that we're looking at. Finally, we can do our sort of logic here to do, figure out whether things are there. So we can say if C is equal to L, so if the character is L and occupied equals 0, in that case it becomes occupied. So we'll do, we also need new line equals this. So then we can do new line dot append occupied. Otherwise, if C is equal to the octothorpe and occupied is greater than or equal to 4, then we can do new line dot append L, so that's where it becomes unoccupied. Otherwise, it remains the same. So we can say else new line dot append C. And so this loop, a lot of code here, this loop builds up each individual line. So after we've built up the individual line, we can do lines dot append new line. And then finally, we want to check if we're at our termination condition. So we can say if lines equals prev, then return, we need to count all of the occupied things inside of this. So return sum C equals this for line in lines for C in line. And so again, we're doing a double loop in this comprehension here. If I remember, I will link a video about comprehensions. This is basically like, a first level nesting of a loop and then a second level nesting of a loop. Otherwise, if lines are not equal, then prev is equal to lines, and we'll just continually loop through this until this condition is met. I think this is correct. Let me run this and see if that is the case after I fix my syntax errors. This is actually different than how I solved this. 43. We have a bug here. All right, so let's figure out our bug. Let me look for some of the common stuff that I messed up before. Okay, so one way to debug this is to put a breakpoint at each stopping point and to print out the lines. That way we can see how this is supposed to execute. So actually we should do pp lines. pp is for pretty printing. I believe that's right. Let me actually pause and get my debug. Well, actually we can just grab it from the puzzle, right? adventofcode.com/2020/11. That's not the URL. 11. Okay, so that's what it should look like after the second round. And ours is not correct. There's some interspersed stuff in here. Weird. Oh, this condition is wrong. I see. This is supposed to be, and not dy equals 0 and, oh, we can actually just say, and not, y, sub I comma x sub I does not equal y comma x. So I had the wrong condition here. We're testing that the things are not equal to the origin point. So let's remove that breakpoint since I'm pretty sure that was the only bug. And we get 37. Okay, cool. So this is kind of the most basic solution that I thought of for part 1. I'm actually going to take this and copy it, and we're going to implement a second solution for part 1 because it's going to make part 2 a little bit easier. So a second solution here, instead of counting every position we're at, we can kind of think about this map as a graph of these occupied points. And we know that if we're at this position or any position around an occupied point, then we can increment the occupied count there. So what I'm going to do instead is build up a map of the size or the counts of things, and then we're going to be able to very quickly check the occupied count for those. Let's do that here. So actually, we're going to have 2 sets of these for loops here. So I'm going to copy this down here. And we need the occupied count. And I'm going to use a collections.counter here. Collections.counter. We need to import collections. And we're going to basically count at each coordinate pair whether there's whether there's a octothorpe or not. So we loop through each of these, and if C is equal to this octothorpe, then we're going to loop around it and set each of the marked positions around here as occupied. So we're going to increment its count. So actually remove that there, and we're going to say occupied y sub I x sub I plus equals 1. So this will give us a map of the bordering things around each of these hashes there. And then down here, we can access our occupied count for y and x directly. And we don't need to do any special looping here. So this kind of pre-calculates a lot of the problems so that the latter part is easier to implement. And let's see if that still works. No, it does not. We've gotten too big here. It's not equal yx. Oh. Oh, I'm looking at the wrong one. I am looking at the wrong set of code here. If it is this, for the difference in those two, get the offset, skip the current one, make sure it's in bounds, increment. Weird. Let's put a breakpoint here and look at our occupied table. Actually, that's going to be too noisy, so let's look at... Oops. Let's look at one execution of it. Oh, I'm confusing myself because there's 2 functions. Breakpoints. Let's look at it here. What did I just do? Why is it now 0? Oh my, what have I done? Let me pause and debug this a little bit. Okay, I found the bug. I was editing the wrong function. I was supposed to edit this down here, not the one above. Yx, I think that's our bug. Yeah, cool, now we get 37 like we expect. But anyway, this does a bunch of work up front. Talking about algorithmic efficiency here, because this loop could technically go forever, this is really an unbounded execution. Although I think the set of rules make it so that it's actually like linear on the size of the thing. But we have a double for loop here, so this is always going to be n squared. Note that this, we actually have a quad for loop, but note that this is a constant time overhead. But anyway, that's how I did part 1. I actually didn't do it this way. I did it the slower way above, but with more gross code. But we're going to take this and go to part 2 and solve part 2 similarly. Part 2... Toppi. And so let me just paste this in here. And part 2 changes the problem in 2 small ways. One is this becomes 5. So we need to set this to 5. And the other thing is how we're marking whether something is occupied. So we actually have vision outwards from all of these octothorpes. So instead of an if condition here, we're actually going to be using a while condition. And we're going to loop outwards from each of those. But it's basically going to look the same structure as we had before. So what we're going to do here is while, and then a whole bunch of conditions here. So we have several termination conditions here. One is the new character, or the new position is a unoccupied or occupied seat, or we have gone out of bounds. So one of those two conditions has to happen for this while loop to terminate. And we also want to skip, so if dy equals dx equals 0, we're just going to skip here. It's going to make us easier to think about here. Okay, so while this is one of our conditions, while it's inbounds and prev y sub I x sub I is equal to a dot. So while we're looking at an aisle, then we will continue to increment x sub I and y sub I by doing this. And then finally we need to check again this same thing down here and make sure that we're inbounds and increment occupied. So this is kind of a loop that's just like traversing out in each of the directions. And yeah, we adjusted this to 5, and I think that's the right way to do this. Let's see if I forgot something. Oh, I forgot to import collections. Collections. It is running forever. So I have messed something up here. Oh. This should be y sub I and x sub I. I actually made that same bug when I implemented this the first time. Okay, 26. And that's what we expect. But anyway, that's part 2. You can see how it was pretty easy to adapt it from a smarter part 1 solution. But again, this is, you know, kind of a little ugly. But let's look at the runtime of this. Again, like this is going to dominate the runtime. This is n squared here. This is bounded by n, so you could kind of think of this as being at absolute worst n cubed. Because like you can imagine if you're in the top right corner, you could potentially go out the entire width of your puzzle. But that seems unlikely. But anyway, that's the solution. And I couldn't think of a smarter way to do this. There probably is a smarter way to do this by using graphs and only looking at, you know, particular character set and mapping them out, but I didn't have time to implement that, so these are the solutions you get. But anyway, hopefully this was helpful, and I will see you in the next one.